Hi, welcome to module 14. In module 13 I talked about basic blocks. So I said there are four kinds of basic blocks in combinational circuits, namely decoders, encoders, multiplexers and demultiplexers. In this module we will see what multiplexers are. So a multiplexer in English means you are sharing something, right. So you might have seen movie multiplexes, for instance, movie theaters which are multiplexes. So the word multiplex means many in one, right, that is what it essentially means. So what we will have when we say multiplexing is we want to transmit a large number of information units on a small number of lines. This multiplexing is there in telephone lines and several other things. In fact, I introduced the term multiplexer in a previous module where I said there are symbols, Boolean equations and so on. I briefly mentioned this term multiplexer. A digital multiplexer selects binary information from one of the many input lines and it will redirect it to a single output line. So imagine there are 3 or 4 of us in a neighborhood and there is only one telephone line that is going out of the neighborhood. So 4 of us, if we want to connect to the telephone line, we will put what is called a multiplexer there, and based on what is given as a control to the multiplexer, exactly one of the telephone lines will be connected to the output. So you can see a picture below. So imagine these are the 4 houses in the neighborhood and there is a multiplexer sitting there. If an appropriate control is given, one of these 4 will be connected to the output, and as long as the control is held at that, only one input is given to the output, the other inputs cannot be connected. If you want the other inputs to be connected, you have to change the control to something else. So in this example, if S1 is on and S0 is on, let us assume that this switch will switch to D3, which means the output will start tracking D3. If S1 is 1 and if S0 is 0, then output will start tracking D2. The switch will come to this position and output will start tracking D2 and so on. So this is what we want from a multiplexer, and if you want to put this in a table, this is the way to do it. So you have S1 and S0, these are the control lines. So there are 4 different control values that are possible, namely 0, 0, 0, 1, 1, 0 and 1, 1, and the output should follow either D0, D1, D2 or D3 depending on the input combinations. So remember, D0 or D1, D2, D3 themselves can be 0 or 1. We do not really care about whether D0 is 0 or 1, D1 is 0 or 1 and so on. As long as the control is 0, 0, in the single bit multiplexer, the output is a single bit, the inputs are all single bits at a time. There are 4 inputs in this example, but each one of them is a single bit, and we do not care whether the bit is 0 or 1. All we care about is based on the control line, which the output should be connected to which input and which one should be detached from. So you connect to 1 and detach from 3, and if you notice at all points of time the switch will be connected to one of them at least, in fact exactly one of them. You cannot say I will not connect it to any of them. So a multiplexer is not that, because you have only 4 combinations. Of the 4 combinations, multiplexer demands that one of the inputs is connected always, and outside the 4 combinations there is nothing else. So this is what is called a variable entered map. This is like a K map, only that we did not put D0, D1, D2, D3 as 4 different columns and wrote output based on that. Since we do not really care about what value D0 or D1 takes, we just put D0 here directly. So a way to do that in a K map is as follows. So when 0, 0 is, so this is the way I should interpret this K map. If S1 is 0 and S0 is 0, output is the same as D0. If S1 is 0 and output is, sorry, if S1 is 0 and if S0 is 1, output should follow D1 and so on. That is the way we should read this table. So we do not care about zeros or ones within the K map here. So this is a 4 to 1 multiplexer. It has 4 inputs, it has 1 output. In some sense this is resembling like what we had in a encoder, right. It had 2 power n inputs, right, but then an encoder will have, if you have 2 power n inputs, it will have n outputs. In a multiplexer you have 2 power n inputs, you have only 1 output. So that is the difference between an encoder and a multiplexer. So it has only 1 output in this one. in multiplexers. So we will call this a data selector. There are 2 power n data inputs and we have n select lines. As before, we will not count the control lines when we say it is a multiplexer. So if I say 4 to 1 multiplexer, it is 4 different inputs connected to one output. The control lines, the count of the control lines is not taken into account there. So there are 4 inputs, n select lines and 1 output line. We will call this a 2 power n is to 1 multiplexer. So let us see the simplest of the multiplexers. The simplest of them is a 2 to 1 multiplexer. So here we have a 2 to 1 multiplexer. This is the symbol, I showed the symbol earlier also. This is a symbol we are going to use for multiplexer. So the control line will come on this edge of the trapezoid. So you see that there is a long edge, there is a short edge which are parallel and there are these 2 crooked edges. So a control line will come to one of these slanted edges. In the longer side is supposed to be corresponding to the inputs and the shorter side of the trapezoid is supposed to correspond to the output. So you can see that this, if you imagine this as a black box, it is 3 inputs W0, W1 and S and there is one output F. And what we want is, if the select line is 0, we want W0 to be transferred to F. If the select line is 1, we want W1 to be transferred to F. So we will put the symbol 0 and 1 to indicate which one is supposed to be for S equal to 0 and which one is supposed to be for S equal to 1. This table makes it clear. When S is 0, we want W0 to be transferred to F, and when S is 1, we want W1 to be transferred to F. So these 2 symbols here tell us for which combination, for which value of S this one should be passed to the output. So this is the graphical symbol and this is the truth table and this is the implementation in sum of products form. So let's interpret this in an English sentence. If S is off, then you can see that W0, so if S is off, then the inverter will have it 1 here, 1 and W0 will be W0 here. If S is 0, sorry, if S is 1, this will be 0, this will be 1 and you will have 1 into W1 here. So if S is 1, you will have W1 here, if S is 0, you will have W0 here and you are logically ORing these 2. So as an expression, what we have is S, you can see that here also. So S, we can write F in terms of S, W0 and W1. F, function F is S bar into W0 plus S into W1. So F is, I will again repeat this, F is S bar into W0 plus S into W1. We saw this equation earlier also. We will call this S as a select line and W0 and W1 are the data lines. So we will see a 4 to 1 mux here. The internal structure of a 4 to 1 mux looks like this. So we have 2 inputs S1 and S0 which are control inputs and we have the 4 data inputs D0, D1, D2 and D3, and what we are going to do is we are going to take all the 4 combinations of S1 and S0. So if you put the inverter here, right, if you put the 2 inverters here, at least S1, S0 you will get 4 different combinations and you have one AND gate for each one of the data lines. So if you look at these 2, they are coming from S1 complement and S0 complement. If you look at these 2 lines here in the second AND gate, the 2 lines in the bottom of the second AND gate, you will see that S1 is coming from off and so S1 is coming from off and S0 is coming from 1. You will see that here, see it is coming from 1. Then for the last line, it is tapped from S1 being on and S0 being on. And this AND gate is ANDing with D0, D1, D2 or D3 and 4 of these are connected to a single 4 input OR gate and then you have an output. So essentially what this is doing is, if you go and look at the output, so it has 4 inputs here and 1 output here, it is a 4 to 1 multiplexer. So a 4 to 1 multiplexer will have 2 select lines, 4 data lines and 1 output. And because we have the select lines here, exactly one of these AND gates will be on, the other ones will give us 0 and whichever is on will pass on D0 to out. You can find that out by looking at, so try and put S1 equals 0 and S0 equals 1, see which of the gates is turning on, you will see that exactly one of the AND gates will turn on, and that AND gate will also copy the corresponding input to the input of the OR gate. So OR gate will see 3 zeros and the data input, one of these data inputs here. So the data input or zeros is the data input itself, that you will see in the output. So this is the internal structure of a 4 to 1 mux. So one thing that this circuit has is, it has a remarkable uncanny resemblance to the decoder that we saw earlier. So we will come to that in a little while. So a 2 power n to 1 mux needs 2 power n plus 1 input AND gates. So we have, so this is a 4 to 1 multiplexer, it requires n plus 1 input AND gates. How many of, so it requires 2 power n is the count and n plus 1 is the number of inputs. It requires 4 2 plus 1 or 3 input AND gates for selection and a single 2 power n input OR gate to generate the final output. Okay. So this is the description of a mux. Like I said, this circuit has a remarkable closeness to the decoders. So this is the circuit for a mux, and I am going to convert this to a decoder. Let us see how to do this. The first thing I am going to do is, instead of the 4 data lines that we had earlier, I am going to connect all of them together and I am going to call that enable, right. So I am going to call that enable, and if I get rid of the OR gate, then I will have 4 output lines, and this is actually a picture of a decoder, right. A decoder is one in which you have a single enable line and you have 4 output lines for 2 input combinations. If there are 2 input combinations, you will have 4 outputs. This is actually a decoder. So if you want to get a decoder from a mux, you have to connect all the inputs together, and somehow if you are able to remove the OR gate and keep the 4 input lines to the OR gate as it is, then you will get a decoder. The reverse, if you want to get a mux from a decoder, then you put a single OR gate here and do not connect the same line to all the inputs, instead leave them as 4 separate inputs. So that will give you a mux. So you can see the picture. So when you remove the OR gate, right, this is a decoder with 4 separate input lines, and with the OR gate it is a multiplexer. So they are very closely connected. So let us look at how to use muxes, or what are the expressions for muxes. So I said that earlier, now I will say that explicitly. A 2 to 1 mux has this expression. If I have one select line called S, if S is off, then you will see that this expression is, so if S is off, then S is 0, then 0 bar is 1, 1 into D naught. However, this term will become 0. So 1 and D naught is D naught. If S is 1, this term will be 0, this term will be D1. So that is the expression for a 2 to 1 mux. So now I want you to go and think about a little bit about what the expression for a 4 to 1 mux is. I am going to show that in a little while, but you go and think about it. So it should have 2 select lines S1 and S0, 4 data lines D0, D1, D2, D3, and one single output line called out. It will take a while to think about what the expression is going to be. So the expression is as follows. If S1 bar, S0 bar corresponds to both of them being off, if both are off, pass on D0, if S1 is off, S0 is on, pass on D1, if S1 is on, S0 is off, pass on D2, and if both of them are on, pass on D3. So you can see that the structure is very similar to what you had here. So here you had 2 values, 2 combinations for a single input line S. Here you have 4 possible combinations, S1, S0 both complemented and only one of them complemented and both not complemented. So in the general expression is out as a Boolean expression is the logical OR over 2 power n terms starting from 0 to 2 power n minus 1, mi which is the min term I, and data I which is the ith line of data. So mi is the ith min term, you take the ith min term and it with data input I, and you do it for all the 2 power n combinations, you put a single OR gate with 2 power n inputs, that will give you the output. This is the general expression for a 2 to 1 mux. So go and think about what the expression for a 3 to 1 mux is, for instance. Go and write it down and check whether it is correct or not. Now let us see how to do various things with muxes. the first thing I am going to show, as I did earlier with decoders, is I am going to use a smaller mux, namely a 2 to 1 mux, to build a larger mux, namely a 4 to 1 mux. So let us take stock of the situation first. What does a 4 to 1 mux need? A 4 to 1 mux needs 2 control inputs, 4 data inputs and 1 output. So if you imagine a box around this now, this circuit will take S1 and S0, which are the 2 control inputs, and it takes 4 data inputs W0, W1, W2, W3, and there is a single output F. So you can think of it as a black box around it, and we want to design a circuit like this. So to be able to do that, right, so this is a circuit which does it. So let us see how it is. So now let us imagine that S1 is on. If S1 is on, right, whatever is in this line will be passed to F, and whatever is in this line will not be. So if S1 is on, this line, this mux's output, the one in the bottom, its output will be passed on to F. Now let us see what are the conditions under which these inputs are going to come. So where is this going to come? If S0 is 0, then W2 will be on this line. If S0 is 1, then W3 will be on this line, right. That is the meaning of this 2 to 1 mux, right. It is taking S0 as a select line. If S0 is 0, then W2 will be here. If S0 is 1, W3 will be here, right. And if you want this to be passed down to here, S1 should be 1. So you can go from the left side to right side and see the conditions under which F gets various terms. If you want W0 to be passed down to F, we want S0 to be 0, so that this line will take W0, and we want S1 to be 0, so that this line will be going to the output. So we want both these to be 0 for W0 to go to the output. If you want W3 to go to the output, both of them should be 1, and if you want, let us say, W1 to go to the output, you can see that S1 should be 1, so that W1 comes here, and S0 should be 0, so that it comes here, right. So the combination you need for W1 to go to F is S1 is 1 and S0 is 0. So this is a 4 to 1 mux, but internally we have 2 to 1 muxes used for that. So a practical application for a multiplexer is actually what is called a crossbar switch. So let us say there are 2 people on the other side of the telephone line. So there are 2 people who want to make phone calls, and there are 2 people who can receive the phone calls, and whoever is calling should be able to call both of them. This is what we want, right. So there are 2 people trying to make phone calls, and there are 2 people who can receive them. We want to be able to make any one of them connect to any one of them. So such a circuit is called a crossbar switch. So a crossbar switch is one in which any of the inputs can connect to any of the outputs based on what is the select. So this is a very useful application, because you will see this in telephone switches and inside circuits and so on. The internal implementation of a crossbar switch is as follows. So you use 2 muxes, a mux on the top and mux in the bottom, and it takes one external line called the control line, which is select, and there are 2 inputs x1 and x2. So what we want is, if S is 0, so let us look at what happens when S is 0. If S is 0, x1 will be passed on to y1 and x2 will be passed on to y2, because if you put x is equal to 0, look at which line is connected. X2 is connected to the 0th pin, and here x1 is connected to the 0th pin of this mux. So if S is 0, x1 will be connected to y1 and x2 will be tracked by y2. However, if S1 is 1, then x2 will be passed on to y1 and x1 will be passed on to y2. So this is a simple circuit which actually does what is called a crossbar. So the name crossbar comes because of this cross connected fashion you have. You do not have lines going from x1 to y1 and x2 to y2. You also have this cross connection or X connection that is there, which is needed for this crossbar switch, and this is a circuit which actually does the crossbar. So if you want a crossbar like this, you need 2 muxes which can take care of it. So one thing I want you to go and think about is how to design a 4x4 crossbar. So 4x4 crossbar will have 4 inputs here and 4 outputs here, you should be able to connect any 4 to any 4 here, and you should have an appropriate number of select lines. So go and think about how many select lines you need for this. You also go and think about how to design that using a mux. So now let us move on to how to use a mux as a logic circuit. So muxes are sometimes called hardware lookup tables. We will see then why it is carrying the name called lookup table. To implement a n variable function, you can actually take a 2 power n to 1 mux, which means it has 2 power n select lines n 2 power n data lines, n select lines, and 1 output. That is a 2 power n is to 1 mux. You can implement any n variable function using a 2 to the n to 1 mux. So what we will do is we will connect the 2 to 1 mux, the n input variables. So we will plug the truth table in some sense at the inputs, we will plug the n input variables to the select lines, and the output will be the corresponding output. So I will show a picture in a little while. So you use a 2 power n is to 1 mux, connect the n input variables to the n select lines in the what is called the most significant bit to the least significant bit order. So I always mention this, right, f of x y z means x is the first leftmost column, y is the next column, z is the next column, and so on. So if I write f of x y z, then x is the most significant bit and z is the least significant bit. So from left to right, when you look at it, whatever is the leftmost is the most significant and whatever is the rightmost is the least significant. So that is how we do it in decimals also. If I tell you number 756, then 7 is the most significant, it has higher weight, it carries a weight of 100, and 6 is the least significant, it has weight 1. So left to right is what we have as most significant to least significant. So what we will do is we will wire the mux in such a way that we will, so I will show you the circuit. Let's take a small example, I will come to that bullet in a little while. So if you want to implement a function f of a comma b comma c, which is sigma of 1, 2, 4 and 7, let us see how to do that. So I am going to take a demultiplexer. So the first thing we notice is the minterm is going up to minterm 7. A minterm 7 will happen only for a 3 input circuit, right. So we have 3 inputs here, a, b and c. So we give a, b and c as the select lines s2, s1 and s0. So that is what I said. So a, b, c is in the left to right order, and the select lines s2 is more significant than s1 is more significant than s0 in this order. And what we are going to do is, let us see the minterms here. So minterm 1 is here, so you take d1 input, put 1 there. Minterm 2 we want, so take d2 input, put 1 there. We want minterm 4 is here, so take d4 input, put a 1, and 7 take d7 input and put a 1. So if we go and look at this, this is the truth table for the circuit. So the truth table will actually have this combination 0 1 1 0 1 0 0 1. So you plug in the truth table in the 2 power n is to 1 multiplexer as the input lines, various, so this is these are all constants, right, there are no variables here, these are all constants. The actual a, b, c, which are the input conditions, you plug them here and the output is the expected output. So you can imagine how this is going to work. So so let us say I have a, b, c as 1 0 1, right. If a is 1, b is 0, c is 1, it is supposed to pass on the d5th line to the output, but what does the d5th line have? It has 0 at the input, so f will be 0. So you can see that 5 is not in the expression CSOP here. So when this is 1, this is 0 and this is 1, d5 which has input 0 will be passed to the output. If I want, let us say if I put a equal to 0, b equal to 1 and c equal to 1, so that corresponds to the condition 0 1 1 or 3. So d3 should be passed on to output or 0 will be passed on to the output. So this is a mux based circuit for a truth table. So what we need, why we call this a lookup table is as follows. You take any generic mux, you put the inputs in the order that you want, find out the truth table that you want for the function, plug it in the set of data inputs, you are done, that is it, no more design, you do not have to do anything more. All you have to do is take the 3 variables in this case and take the function that you want, stick its truth table at the inputs, you are done. So if I gave you the truth table, let us say I gave you a truth table 1 3 5 7 instead of 1 2 4 7, let us say I gave you 1 3 5 7, all you have to do is make D1 on, D3 on, D5 on and D7 on, the rest of them 0, that's the circuit that you want. It's as simple as that. So this is called mux based logic design. In mux based logic, the advantage is that it's very easy to design the circuit, because all you have to do is find out the truth table and stick it in. It's easier to debug the circuits using multiplexers. If you want to find out if there is any fault in it, there is no minimization, nothing, right? You have a circuit and if you put the truth table, you are done. So there is you will not go wrong too many times. However, it comes with a disadvantage. The problem is that muxes can become very large for a large number of inputs. So in this case, we didn't do any minimization. So there is some structure to the problem here. We didn't see any structure, we didn't minimize anything, we just stuck the truth table here. So the circuit may get very complicated. You may actually spend more to do simple functions even. So mux based design is okay for very small circuits, it's not good for larger circuits. So normally if you have a function which has more than 4 variables, then you don't usually use a mux based thing. So you can't use a single multiplexer for this, you can use a combination of multiplexers, but a single multiplexer becomes prohibitively expensive the moment the number of inputs goes to more than 4. So what you typically do is you use what is called a multiplexer tree. So a multiplexer tree is one in which you have smaller muxes instead of the larger mux. So I will show you a quick picture for this circuit. So f of a comma b comma c actually demands a 8:1 mux, but instead of using a 8:1 mux, you can use either 2:1 muxes like this or 4:1 muxes like this to get the corresponding output. So what we have done is we have arranged a tree of multiplexers here. So there are 4 2:1 muxes followed by 2 2:1 mux followed by 1 2:1 mux, and we stick the truth table as we had for previous case, but now these are all smaller multiplexers rather than one huge monolithic 8:1 multiplexer. Similarly, we have 3 4:1 multiplexers as opposed to one huge 8:1 multiplexer. So I will not get into the details of this. It's possible to take smaller multiplexers and design larger multiplexers. I already showed you that. So this one is essentially expanding on the idea for 8 inputs. So this brings me to the end of this module. So what we have seen in this module is this very basic circuit called multiplexer, and we saw what comes with the multiplexer. So the multiplexer is a very useful logic block. In the next module we will see some of the interesting properties of a multiplexer. We will also see various ways in which we can use a multiplexer. So most importantly, in the next lecture we will see the notion of universality of a multiplexer. So multiplexer is actually a universal gate. We will see why it is so in the next class. We will also see some important examples which show how to use a multiplexer, and we end up with one important theorem called Shannon's theorem in the next module. So thank you for now and see you in a little while.